The San Andreas does not end at the Mexican border. It never did. This past Tuesday, a shallow magnitude 6.0 earthquake tore through the Gulf of California. And geologically, that is the same fault. It sits on the southern end of the very boundary that runs beneath Los Angeles, and it struck while a new analysis says the faults up north are wound tighter than at any time in 1,000 years. Stay with me, and you'll know whether this was the trigger California has been dreading, or the warning it can still use. This past Tuesday, at about 1:45 in the afternoon local time, the floor of the Gulf of California tore loose. A magnitude 6.0 earthquake, some agencies put it as high as 6.1, ruptured offshore in the southern Gulf, the long, narrow arm of sea that separates the Baja California Peninsula from mainland Mexico. The epicenter sat northeast of La Paz, roughly 75 kilometers south-southwest of the coastal town of El Progreso on the Sinaloa side. Residents across northwestern Mexico felt the ground move, and in coastal towns, people walked out of their homes and into the streets and waited. Almost immediately, the story went away. There was no tsunami. The United States Geological Survey tagged the event with a green alert, meaning it expected little in the way of casualties or serious damage. No wave, no mass destruction. A green dot on a map. By nightfall, most of the world had already moved on. Mexico had a moderate offshore earthquake. These things happen. Nothing to see here. That reading of it misses the single most important fact about this earthquake. The story of this quake is not the shaking it caused in Mexico. The story is where it happened, what fault it happened on, and what that fault is physically wired into several hundred kilometers to the north, under the feet of more than 20 million people in Southern California. This rupture did not occur on some isolated, faraway fault. It occurred on the southern end of the exact same plate boundary that, farther north, carries a much more famous name, the San Andreas. That is what this is about. Not a minor Mexican earthquake, but a movement on California's own fault system. At a moment when scientists say that system is more dangerously loaded than it has been in 1,000 years. The most important number attached to this earthquake, after the magnitude, is its depth. This rupture happened only about 10 kilometers down, roughly 6 miles beneath the seafloor. In seismology, how far underground a quake begins is one of the biggest factors in how hard it hits the surface. A rupture that starts far below the crust has to push its energy up through kilometers of rock, and that rock absorbs and scatters much of the shaking along the way. A shallow rupture does the opposite. It delivers its energy to the surface almost undiluted, with very little to soften the blow. At 10 kilometers, this was a shallow earthquake. On land, a shallow magnitude 6 can crack walls, drop ceilings, and hurt people. So why did this one do so little? The answer is not depth. The answer is water and distance. The epicenter was offshore, out in the Gulf, and the stretch of sea and open space between the rupture and the nearest towns acted as a buffer, bleeding off the strongest shaking before it ever reached a building. Move that exact same rupture, same magnitude, same shallow depth, underneath a populated inland city, and we would be talking about a very different Tuesday. That distinction matters because it previews the whole story. This was a shallow, energetic, near-miss earthquake spared from being a disaster by geography rather than by being weak. And it did not come alone. This magnitude 6 was not a single, clean jolt. It was the largest shock in a tight cluster of earthquakes that hammered the same stretch of the Gulf inside roughly 24 hours. Alongside the main event, seismographs logged a second shock near magnitude 6, a magnitude 5.3 out in the Gulf, another magnitude 5.3 closer to El Progreso, and a magnitude 4.5 offshore of Topolobampo. That is not the signature of a quiet fault that slipped once and went back to sleep. That is a segment of the Earth's crust actively, violently rearranging itself. On a boundary that is being pulled apart as well as sheared, that kind of multi-shock burst is the norm rather than the exception. A whole neighborhood of small faults failing in sequence, as the strain hunts for the weakest path. What it tells seismologists is that this stretch of the Gulf is not resting. It is deforming in real time. The main shock was large enough to register on seismographs hundreds and even thousands of kilometers away, on instruments in Southern California, including stations near San Diego and on the central San Andreas at Parkfield, and on machines as far off as Japan. For a shallow magnitude 6, that reach is not remarkable on its own, but it is a physical reminder that the energy from this rupture did not stay politely in Mexico. It rippled outward, across the border, along the very fault system it belongs to. To understand why that should get your attention, you have to throw out the map you think you know. If you picture the San Andreas Fault, you probably picture a single line running up through California and then simply stopping somewhere around the Mexican border. That picture is wrong. It is a mapmaker's convention, not geology. Plate boundaries do not stop at national borders, and the San Andreas does not end in the south. It transforms into something else. What runs through California is the boundary between two of the largest tectonic plates on the planet, the Pacific Plate, grinding to the northwest, and the North American Plate, moving to the southeast. These two plates slide past each other at roughly 45 to 50 millimeters a year, about the rate your fingernails grow. Follow that boundary south, past the Imperial Valley, and it crosses into Mexico and enters the Gulf of California. Here, the machinery changes. Instead of the two plates only sliding past one another, they are also pulling apart. This is the Gulf of California Rift, a young ocean basin being born, a staircase of short seafloor spreading centers linked together by long transform faults, where molten rock rises from below to create brand new crust, and the faults between segments snap often and hard. Here is the part that should reframe the entire story for you. The Gulf of California Rift, the Imperial Fault, the San Jacinto Fault, and the San Andreas are not separate, unrelated features. They are all segments of one continuous plate boundary, a single tectonic conveyor belt of Pacific versus North American motion, running unbroken from the Gulf up into California. An earthquake on the Gulf portion of that boundary is, in a real mechanical sense, connected to the San Andreas. It is not a distant foreign event. It is the southern end of California's own fault machine, moving. And when one end of a connected boundary shifts and releases strain, that stress does not vanish. It redistributes along the system. Every time the Gulf moves, the balance of pressure on the segments to the north changes. The fact that this quake produced no tsunami is not a footnote. It is actually a clue that points straight back at California. Big tsunamis are made by a specific kind of earthquake, a megathrust rupture on a subduction zone where one plate dives beneath another and violently lifts or drops an enormous slab of seafloor, shoving the entire water column above it. That vertical heave is what launches a wave. The Gulf of California does not work that way, and neither does the San Andreas. These are transform boundaries. The two sides slide horizontally past each other. They do not stack one on top of the other. Horizontal sideways motion barely disturbs the water above it, so even a strong offshore quake here tends to produce little or no tsunami. That is why the coast was spared. But notice what that tells us. The Gulf is a shearing, sideways slipping, pulling apart boundary, which is exactly the kind of boundary the San Andreas is. The missing tsunami is not evidence that this was a minor event. It is confirmation that the Gulf and the San Andreas are the same kind of beast. So the earthquake was shallow, energetic, part of a cluster, and sitting on California's own plate boundary, which leads to the question everyone in Southern California actually wants answered. Could a magnitude 6 in the Gulf of California set off the long-feared great earthquake on the San Andreas? This is the question at the center of everything, and it deserves an honest two-part answer, because the truth is more interesting than a simple yes or no. The direct answer is no. A magnitude 6 releases a large amount of energy, but it releases it locally, and its epicenter sits hundreds of kilometers south of the dangerous locked segments of the San Andreas in California. Seismic energy fades fast with distance. The physical shock from this Gulf rupture simply does not carry enough force to reach up under Los Angeles or Palm Springs and instantly snap the rock there. Any seismologist will tell you plainly, this quake did not break the San Andreas, and nobody should be bracing for a same-day chain reaction. If that is the fear, you can set it down. There is a longer answer, though, and it is the part that keeps scientists watching. Because it can't instantly snap the fault is not the same as it can't matter at all. There are two real documented mechanisms by which a distant earthquake can influence a faraway fault, and both of them are on the table here. The first is called dynamic triggering. When a significant earthquake happens, its seismic waves travel outward through the crust like ripples, and those passing waves can act as a kind of nudge on distant faults. If a fault is already strained to its limit, imagine a glass sitting right on the very edge of a table. Even a small, well-timed vibration can be enough to tip it over. This is not a theory. Seismologists have watched it happen. Southern California's Imperial Valley, in particular, has repeatedly lit up with swarms of small earthquakes in the hours after strong Gulf of California quakes. And in 1992, the magnitude 7.3 Landers earthquake famously set off bursts of seismic activity across enormous distances, far beyond where its direct energy should have reached. The lesson from Landers was not that distant triggering is common, it usually is not, but that it is possible, and that the faults most likely to answer a passing seismic wave are precisely the ones already sitting at the edge of failure. A relaxed fault absorbs the vibration and does nothing. A critically loaded fault is a different story. The second mechanism is slower and quieter, and it is called static stress transfer. Think of the plate boundary as a single connected chain. When the southern end, the Gulf, releases its tension by rupturing, it does not necessarily relax the whole chain. Depending on the geometry, letting go in the south can actually load the locked segments to the north a little more heavily, pressing on them harder. In that sense, this Tuesday's earthquake did not snap anything in California. But on a fault system that scientists say is already carrying more stress than it has in 1,000 years, it may have added one more small increment of weight to a scale that is already overloaded. That word, overloaded, is where this story goes from unsettling to genuinely alarming because of what a new analysis says about the state of the faults up north. This earthquake did not strike a calm, relaxed fault system. According to a recently published analysis of tectonic stress in Southern California, work that measured decades of ground deformation and compared it against the historical record of past ruptures, the Southern San Andreas Fault and its neighbor, the San Jacinto Fault, have now accumulated their highest levels of stress in over 1,000 years. The analysis does not describe these faults as merely strained. It describes them as critically loaded, pushed right up against the threshold where they fail. That conclusion did not come from a hunch. It came from years of satellite and ground measurements tracking how the crust of Southern California is straining and shifting, matched against the geologic record of when these faults have broken before. When the strain the ground has quietly banked outruns the strain released by the last rupture by the widest margin in 10 centuries. That is what highest in 1,000 years actually means. It is a measurement, not a mood. The simplest way to picture it is a spring being compressed. For roughly 10 centuries, the Pacific Plate has kept pushing northwest, while the locked surfaces of these faults have refused to slip, storing all of that motion as elastic energy, winding tighter and tighter. The longer a fault stays locked, the more energy it banks for the day it finally lets go. To put the time scale in human terms, the last time these faults held this much pent-up energy, the Crusades had not yet begun. No modern city, no highway, no population center has ever sat on top of these faults in a state this loaded. We are, all of us, the first. The established record backs up the alarm. The southernmost stretch of the San Andreas, down by the Coachella Valley and the Salton Sea, has not produced a major rupture since roughly the year 1680, more than 3 centuries ago. On average, that segment has historically broken every 180 to 250 years. Do the arithmetic, and it is well past due. Scientists are careful to say that critically loaded and overdue describe elevated probability, not a date on a calendar. Stress tells you a fault is close to failing, not the day it will fail. But the loading is real, it is measured, and it is why a distant magnitude 6 is worth an entire conversation instead of a shrug. Almost all public attention goes to the San Andreas, but among specialists, the fault that generates real unease is the one most people have never heard of, the San Jacinto. It branches off the San Andreas system and cuts directly through some of the most heavily populated inland country in California, through Riverside, San Bernardino, Hemet, and the sprawl of the Inland Empire, trending down toward San Diego. It is the most seismically active fault in Southern California, capable of magnitude 6 and even magnitude 7 earthquakes, and it runs straight beneath neighborhoods, hospitals, freeways, and the infrastructure that tens of millions of people depend on every day. The real danger is not just the San Jacinto rupturing on its own, it is the possibility that the San Jacinto acts as the starter, the fault that goes first and then hands its energy off to the main line. That is where the geography becomes frightening, because the San Andreas and the San Jacinto do not stay safely apart. They come together at a narrow mountain junction north of San Bernardino called Cajon Pass. If you have ever driven Interstate 15 between Los Angeles and Las Vegas, you have gone right through it. That same pass carries major rail lines, aqueducts, and fuel and power lines linking Southern California to the rest of the country. Scientists who model how ruptures travel describe a junction like Cajon Pass as an earthquake gate. Under normal conditions, the geometry of that junction acts as a barrier. A rupture running along one fault hits the intersection, runs out of stress, and stops. The gate stays shut. But rupture modeling shows that when both fault systems are heavily stressed, the gate can swing open. It can become a pathway instead of a wall. A rupture that begins on the San Jacinto could, in that loaded state, blast through Cajon Pass and jump onto the San Andreas, igniting a rupture far longer and an earthquake far larger than either fault could produce alone. Peer-reviewed modeling of that exact junction, published in 2016 in the journal Science Advances, reconstructed a historical earthquake from the year 1812 as just such a joint rupture, tearing through the Cajon Pass region across both faults at once. And because the length of a rupture is tied directly to its magnitude, a cascade like that is precisely what turns a large earthquake into a regional catastrophe. The math of earthquake size is not gentle. Every single step up the magnitude scale represents roughly 32 times more energy released, which means a magnitude 8 does not shake merely a little harder than a magnitude 6. It unleashes on the order of 1,000 times the energy. That is why rupture length is everything. A fault that breaks for a short distance produces a serious earthquake. A fault that breaks for hundreds of kilometers because the gate let it keep running produces a generational one. The scale of such a catastrophe is not a guess. It has actually been modeled. The United States Geological Survey built a public planning scenario called Shakeout around exactly this kind of event. Their hypothetical, a magnitude 7.8 rupture on the southern San Andreas, estimated on the order of 1,800 deaths, around 50,000 injuries, and roughly $200 billion in losses, with the shaking corridor cutting through the length of the fault. That is not a forecast of Tuesday's quake. It is a measured illustration of what the loaded system to the north is capable of, the stakes that a small nudge is nudging. So where does that leave us in the days ahead? In the immediate term, the honest answer is that the most likely outcome is the boring one. The Gulf sequence will most likely settle down, its aftershocks fading along the usual curve. Only a small fraction of earthquakes, somewhere around 5 to 10%, turn out to be foreshocks to something bigger, so the odds favor this being a standalone burst. The specific thing scientists will be watching over the next several days is the Imperial Valley, just north of the border, for exactly the kind of small triggered swarms that Gulf quakes have set off before. If that region stays quiet, this chapter closes quietly. And what would change the picture is not subtle. A sustained climbing sequence instead of a fading one, or a burst of fresh activity jumping north to the Imperial Valley and the Salton Sea onto the segments that actually feed the San Andreas. That is the signal worth watching for, and it is the reason a quiet green dot on a map earned this much attention in the first place. The larger meaning of this earthquake does not depend on what happens this week. This magnitude 6 is not the trigger. It is the reminder. It is the loudest recent signal that the entire boundary, from the spreading centers of the Gulf up through the Imperial Fault, the San Jacinto, the San Andreas, to the gate at Cajon Pass, is one single, connected, critically loaded machine. And that machine is running right now beneath one of the most populated regions in North America. You will see other explanations circulating online in the coming days. That the quake was engineered by some government program, that recent solar flares set it off, that agencies are secretly hiding a prediction of the big one. Set all of that aside. A major earthquake's energy dwarfs anything a facility like that could inject into the crust by many orders of magnitude. There is no physical mechanism by which a solar flare releases tectonic strain in the ground. And far from hiding the danger, the Geological Survey publishes these worst-case scenarios openly, in exercises anyone can read. The real story needs no secret hand. It is simply a plate boundary doing exactly what plate boundaries do, on a fault network that has quietly wound itself to a 1,000-year breaking point. The correct response to this is not panic. It is preparation. The southern San Andreas will rupture again. That is not a matter of if, but of when. And the specialists have said plainly that the region is not ready. The value of a Tuesday earthquake in the Gulf of California is that it points, like a warning light, at the machine to the north while there is still time to look. This quake did not pull the trigger, but it just reminded everyone that the fault is loaded, and that the only real question left is when.